Hi, in one of the previous videos we were looking at building a DC load, and we did a lot of breadboard work and experimentation on the breadboard, and we came up with a fairly good circuit. So what I've done is I've taken that one step further, and I've now built a case and built up the circuit on a strip board so that I can actually get the thing up and running and be able to use it in my lab. One of the things that I came across while I was doing this, though, is I needed to have some kind of display on the front of the panel. Now, I have some inexpensive eBay specials, if you know what I mean, that I got for a few dollars each that have a combined current and voltage sensor in them. The problem is that they are common between the ground of the volts and the ground of the current sensing. And as you've already probably heard, if you've been following along with my videos in the past, you'll know that this is not a good plan. What you really want to do is have a differential current measurement and differential voltage if you can. But at least, you want to have a differential current measurement across your current shunt, because you want to be able to compensate for any cable wiring drops and things like that. Now, what I've discovered with these have two circuits in. They've got one of these little ST micro processors that drive these things. It's rather overkill probably for what they're actually doing, but they have a separate I'm not sure what the device is because I haven't been able to find a data sheet on it or anything, but it looks like it's connected either by SPI or I2C onto the ST microcontroller, and it deals with measuring the current. Now, what they've got is they've got a 25 milliohm shunt on the input to it. It looks like both sides of the shunt go to the input of the device, so I'm assuming it's probably using a differential measurement into the device. But then they've got a resistor that has connected it to the same as the power supply 0, which, for most people that would probably be okay. And they probably did it because maybe they had a few people blowing them up because they were going outside of the common range with the signals or something. But what I discovered is if you disconnect that resistor, just take it out of circuit, you're able to actually use the current side in a differential mode and therefore get a fairly accurate measurement of both the voltage and the current for my DC load. So what I'm going to do is show you right now how to hack this so that you can do the same thing yourself. All right. Now let's have a quick look on the bench, and I'll just draw a quick picture for you to show you basically what we're dealing with, and then we'll do a close-up and I'll show you how to hack this to get it working effectively in a differential mode. So what I'm going to show you is close-up of how these are hooked up on the back and which resistor to remove to allow the current shunt to be able to work in a differential mode, floating from its negative supply rail instead of being tied to the negative supply rail. Then we'll pop it into my DC load and we'll give it a go. So let's get to the bench and I'll just show you a quick diagram of what we've got to start with. Okay, this is a quick diagram of this. You got the two displays. Sorry, it's upside down. Got your voltage display 4-digit and your current display, which is also 4-digit. The one thing about this is the current display actually goes from 0 to 1 amp as 4-digit, and then when you get to 1 amp it actually flips the decimal point and gives you it up to 5 amps. Actually, I think this will go up to more than 5. Anyway, we're using it up to 5 amps. But the point is, it's actually auto-ranging, which means that whatever's measuring the current is switching its gain somehow to increase the dynamic range of this thing. So you actually go down to a microamp when it's on the lower range and down to 1 milliamp when it's on its full amps range. The voltage is just straightforward 0 to 99 volts, so it only goes down to 10 millivolts for measuring. We're not so worried about the voltage, we just want a rough idea of what the voltage is that's across the device so that we can get an idea of the power that's being dissipated in the MOSFET inside. But what we really want is we want the accuracy of the current, and by having this auto-ranging feature, that's quite nice and it gives us what we need. So anyway, what we have inside here is, this is just a very crude block diagram. You've got your positive supply comes in, it goes through a 3.3 volt regulator, feeds the microprocessor, and it also feeds this other device. I've marked it as an ADC programmable gain amplifier down here, but I'm not 100% sure what it is. You have an ST micro processor, microcontroller driving this whole thing, which got multiple analog inputs. And it's got the two 7 segment by 4 displays hooked directly into it, and it's driving it directly from the micro, so there's no other circuitry involved in that. Now, your voltage sense coming in is basically a simple divider network that allows your 0 to 99 volts to be dropped down to probably 0 to 3 volts or something like that for the micro to read on its ADC. But for the current range, what they've done is, rather than have a simple shunt resistor, because they want to keep the shunt value so low, you would have virtually no resolution on your micro A to D converter if you were trying to use it, because you would only be, if it's 25 milliohms or even 50 milliohms, you're only talking about half a volt at best if you were reading 10 amps with a 50 milliohm. They've got a 25 milliohm to minimize the burden voltage on this thing, which means that at best you're going to get, even with 20, with like 10 amps, you're only going to get 250 millivolts across this thing. And so if you were trying to use a microprocessor, microcontroller's ADC, that's going to give you a very, very limited range. So what they've done is they've included a device in here, and it looks similar to some of the Texas Instruments programmable gain amplifier ADC kind of chips, but it's not the same pin out, so I haven't been able to pin down exactly which one it is. I do know that it's connected what appears to be to the SPI lines of the microprocessor here, but it could be I2C or SPI, but based on the pin out of the micro, I think it's probably using SPI, not I2C. And I've noticed also as you increase this at a certain point, there's always this continuous communications going on. It will flip to the new range, which means it's probably telling this PGA to flip to a different gain on an input op amp or something like that that's built into this thing. But one of the things they've done here in their design is that you've got your plus input and your ground, and then your voltage input is also referenced to that same ground, so it's not differentially measuring your volts. Now I can work with that in my design for the DC load, but what the issue is the current input, even though it's going into this PGA ADC device as a differential input, they've put a 0 ohm resistor between the negative side of the current shunt and the ground, which means that if you're trying to measure the voltages with reference to the input terminals of the DC load, but you want to measure the current across the shunt, then you can't do it easily, not without getting errors incurred because of the voltage drop. You're measuring a high current path down here, but because these two are connected together and this is at a different point, you end up introducing other current loops and things in the circuit which you really don't want to have. And the way to get rid of that is to remove this 0 ohm resistor, and that's what I'm going to do to fix this issue for mine. I've shown you the issue on previous videos where we've been looking at ADCs, and I had one where we looked at all of these displays as well, and we kind of talked through the issues that were being seen there. Anyway, let's have a close look at one of these panel meters, and I'll show you where the resistor is and what we need to do to disconnect it. So right off the bat, I'm going to apologize for any focusing issues. I put a macro lens on here and I'm just free holding the display. I've taken it out of its little case here so that you can see better, and I'm just going to manipulate it and zoom in so that I can show you where the resistor is that needs to be removed to get this thing to work in differential mode. So let's just do a quick look at what's on this thing first. So I'm just going to zoom in and turn it over. So this is the back of the board. The switch here allows you to do some fine adjustment of the current measurement to get it more accurate, to compensate a little bit for the lead resistance, but it's not enough and not intelligent enough to be able to get rid of the issues because of the grounding problems. This is the ST microcontroller that drives the whole board. A little bit of a couple of resistor networks here just for current limiting to the displays, a few passive components over here. You've got your 3.3 volt regulator. I think that's on the other side of the board. This here is your 25 milliohm current shunt. This is your current connection, and this is your voltage power supply connection, and also your voltage sense connection. So let's get back to the other side of the board here. All right, you've got your display here, and then at this end, what we've got, if I can just try and get this to focus, there we go, is up the top here we've got the power input, and underneath here is the 3.3 volt regulator and stuff like that, little protection diode. On this side, this little device just here, I don't know if I can zoom in any closer and be able to get focus still. Yep, can. It's a CA2P, and I haven't been able to find a data sheet on it, but if you guys can, that would be great. What we've got is these two pins, this one here and this one here. That's the current shunt on the other side, and you can see this drops down to here and comes over to here, and then this pin comes along into this pin. So the current shunt is actually driving to these N2 pins of this device. Now what we've also got is, you can see from this one, there is this 0 ohm resistor right here just sticking out on the end of the display, and that is the one that is connecting it to the ground of the overall display here, and that's what's causing the issue. So that's what we need to remove to make this PGA device here work in a differential mode, instead of having one, because it is working in differential, but they've tied one end of it to the ground rail, which kind of defeats the whole object. We're going to remove that so that we can work it in differential and get a much more accurate reading and have no interference because of ground loops. So let me just revert back to the normal lens, and we'll just have a go at removing this. So just before I pull the resistor out, I just wanted to show you the resistance values here. Now I haven't, let me just null my meter. Okay, so this is the current shunt. Now this includes the lead resistance as well. I've actually measured this with a different meter, and it is indeed about 25 milliohms. So we're reading about 50 milliohms here, but I'm well outside of the resolution of the meter I've got. Okay, now if I go to the negative supply rail, you'll see that it's actually shorted out. All right, or if I do it on the end of the wire, just to let you know that I'm not cheating here, and go to the negative of this, stop getting my finger resistance and get the lead resistance there. All right, so as you can see, the two grounds are shorted together. So now what we're going to do is remove that resistor, and I'll show you what the difference is. Okay, so I've removed the resistor out of here. I did it a rather rude and crude way, and just used a pair of soldering irons. I just caught the edge of the plastic and melted it slightly, but managed to get it out. It's just enough of it protruding that I could attack it from both sides and lift it off cleanly with a small pointy soldering iron. So that's out. So now let's just check the resistance again. So I'll go from the ground of the power to the ground of the shunt, and this time, as you can see there, we've got about 1.5-ish megohms, which is basically the internal circuitry and stuff like that. But if I measure the shunt still, you'll see that we still have our very, very low value for the shunt, which is 25 milliohms. I just nulled it again. So if I try and null it and see if we can get a better reading. As I say, it's only 25 milliohms, so it's well outside of the range of the meter. There you go, so it's reading 50 again. So we haven't affected the shunt at all. We've removed the ground to the 0 volts. So now if we just get this thing put back in it, we'll power it up and have a quick check to make sure it's functioning properly still, make sure it didn't break anything. Okay, so I've just connected 12 volt power to it, and I've also connected the sense to the 12 volt rail as well, just so we can see what that is doing. And we've got 11.99, and I've set 12, and it's actually reading 11.99 on the power supply as well, so that's pretty good. Let me just try and set exactly 12. 11.99. So that's reading spot on for that. Now let's try some current. So I'm going to use channel 3 of my power supply, and I'll set the current to 0.5 amp just to start with as a current limit, because I'm just going to directly connect it. So it's going to put it into current mode. There you go. That's 0.5 amp on the power supply, and I'm reading 499.5, so that's pretty good. Let's up it to 5 amps on the power supply to go all the way, and you can see there it just shifted and brought the decimal point in, so we got 4.992. so we're reading down to a milliamp right now. That's still fairly close. We could probably correct that a little bit if we wanted to, but it's good enough for what we're doing. The shunt is probably starting to get a little on the warm side, and the only real way to adjust that would be to crimp the shunt slightly. But as I say, that's probably close enough for what we want. Let me just take it back down to 1 amp. You can see there 99. So it's now gone into being able to read down to microamps, but again, pretty accurate. Let's see if I can tweak that a little bit. Just using a pair of cutters to crimp it a little bit on the rail to get it a little bit more accurate. What I'm going to do is use a pair of cutters and just gently nip the current shunt just to tweak its value just a tiny bit. You can see there I've taken it up to 99.999.5. Doesn't take much. There. 1.001, so that's close enough. We've got 1 up there, 1.001 here. Let's see if they fix that on the higher range now. We'll go back up to 5 amps. Alright, so it's within a percent. Yep, 5.004. Let's go down to 0.5 of an amp. Now that's reading 500.3, so that's accurate enough for that. The volts is reading correctly. So there you go. That's pretty much the hack. Now I'm going to go and put this into my DC load and set that up, and we'll have a separate video on going over the DC load and how it works and how it's performing anyway. So all I wanted to show you here was how to do this hack on these little cheap Chinese eBay special dual volt current display, so that you can actually work them in differential. And that's really all there is to it. You just remove that one resistor, and now you've got your current working separate to your voltage range. The 0 volts are no longer tied together. Now the one thing you've got to remember though is due to common mode restrictions on most chips, you want to keep your current shunt inside the range of your voltage. So what I'm going to quickly show you before we finish off the video is how I hook this into my DC load so that we would achieve that. So this is a really simplified view of the DC load. We have an op amp with an input of 0 to 0.5 volts representing our set point desired current, which is 0 to 5 amps. We have a 100 milliohm shunt which is used to measure the current we've got, and the top end of that is fed back into the negative input of the op amp. So if you set 100 millivolts, then you would require 100 millivolts across this 100 milliohm, which would represent 1 amp. Nice and simple. The negative end of the 4-terminal shunt resistor, or one end of it for the voltage measurement, is connected to the analog 0 volts of the op amp and the supply, which is all internal. It's all low current and everything else. The current inputs to the sense resistor, the positive end goes through the MOSFET out to the positive side of the device under test, like a power supply or whatever it might be, and the negative side goes to the negative terminal. So this is our basic circuit. So the question is, how do we insert our current sense panel meter into this? Well, the voltage side is easy enough. We just want to have the voltage actually connected for measuring the volts. We just want to measure the volts like this. All right. So putting in the voltmeter, we've got it. The sense is on the positive input from the device under test, directly connected to the terminal. The negative side, which is also the negative supply, is connected to the negative terminal. I'm just going to make that blue instead. And the positive supply for the meter is connected to the same 12 volt internal supply. Now, this little bit of extra resistance here from the voltage perspective does not make any difference, because it's using the sense between the 12 volt line is just supplying it, but it's actually measuring between the plus rail and the 0, which means we get the correct current. All this will mean is that you're running on a supply of maybe 11.3 or something like that. So it's going to be measuring on a slightly different supply to what the op amp is working on. That has no effect whatsoever. But for the current side, that's a little different, because so what I've done for the current is I've actually put it in between the FET and the 100 milliohm current sense resistor, because what that's doing now is it's sitting the current sense nicely in the middle of the FET and the low side of the current and voltage measurement, so it's not going to interfere with anything. Yes, it introduces 25 milliohms of extra series resistance, but because we're measuring our current feedback directly across here, that has no impact, and we're keeping this low end as close to the 0 volts of the device under test as we can, so that we're minimizing any impact outside here as well. And wiring resistance really doesn't make any difference, because this wire here to the ammeter, or whether it's here, would have no bearing, except that it would start elevating the 100 milliohms slightly from this 0 volts and maybe introduce some stray currents and things. We don't want to do that. Obviously, if the 0 volts of this ammeter, the negative side, which would be here, was connected to the 0 volts of the voltage side, then that wouldn't work. And as you can see, if I connected this ammeter right here, it would have effectively shorted out our shunt resistor. If I put it down here at this part of the circuitry to the terminal, then it would be shorting out the 0 volts and the output of the device under test, the return path. It will be providing an alternate current path to that as well, which also starts to mess things up, as we've seen in previous videos. So the best place I figured to put this thing was actually between the MOSFET and the series shunt resistor, and removing that 0 ohm resistor that was on the panel meter. It allows me to do this without worrying about it. And now I'm also operating this nicely in the middle of the, or not the middle, but near the low end of the differential range, but it's elevated slightly, a little bit above, because of the, depending on the current through here. But now we're not interfering with each other. They're working, because it's differential now in the current, it's working completely separately, or at least, sorry, it's not, it is differential, but also the current side is floating independently of the voltage side. So now it will work nicely and give us accurate readings. So that basically is all we've done. We've now hacked the panel meter to allow us to do this. And that completes the hack video. So if you like it, give me a thumbs up and everything else. If you don't, well, then don't. But anyway, I hope this helps you, because it's a cheap and easy way of getting a low cost but reasonably accurate current and voltage meter into your little DC load. And this will complete the hack video. I will be releasing very, very shortly the video for the completion of the DC load, which will include this hack on the panel meter for it. And that will then complete the video for the DC load, or at least the analog version of it. I will be doing another one later, which will be a complete microprocessor controlled one that will probably augment nicely the work that Ian Scott Johnson is doing on his channel, where he's just completed a DC voltage standard using an Arduino microprocessor based control system and a precision digital to analog converter to do a voltage standard output. What I'm going to be doing is something similar, but instead of a voltage standard, I'll be using it for a current standard. So anyway, stay tuned for that. But in the meantime, that's this one done. So as I say, just to finish off with the DC load, watch out for the next video. Probably be out in a few hours or so after this one to complete the picture. Thanks.